Hi, and welcome to our discussion on atmospheric dynamics. We are going to talk about the thermal wind in this block. And specifically, this is the second video for the thermal wind. So we're going to start right out with the thermal wind equation. And the thermal wind equation is an equation that tells us that the vertical shear of the horizontal wind in a layer is proportional to the horizontal temperature gradient. So looking at this equation, on the left-hand side you have Vt, that's the thermal wind. The thermal wind is the change in wind with height, so it's the vector difference. On the right side of the equation you've got a lot of things. R is the gas constant, F is the Coriolis parameter. P2 and P1 are the two pressures at different altitudes for the layer that you're looking at. The del HT is the horizontal temperature gradient, and it's divided by dz, or dz is the derivative. So it's saying the horizontal temperature gradient in the layer, the temperature gradient in the layer. So the temperature gradient in the layer produces wind shear, and you get a change in wind direction and a change in wind and speed with height. So that's what we just said. With a horizontal temperature gradient, we can get or calculate the horizontal shear. So that's what we're going to do in this video. We're actually going to go through and calculate the thermal wind. So we're going to start out with winds at 850 millibars. Looking at it there, it looks like they're about 30 knots blowing from the west. What are the winds at 300 millibars? Can you figure that out? And according to the equation, you can, because for a temperature gradient in a layer, it'll give you the shear. And if you know how deep that layer is, you can figure out the change in wind and add that to the winds at 850 millibars to get the winds at 300 millibars. So looking down on the weather map, this is what we have. This is an 850 map. North is pointing up. There are a lot of numbers here, but we're looking at winds that are moving at about 30 knots. This is at 43 degrees north latitude, so you can use your 2 omega sine phi to figure out F. Also, your temperature gradient is given. Here the temperature changes 2 degrees Celsius over 100 kilometers. So we're going to use that to calculate the winds up at 300 millibars. So here's our equation. The change in wind with height is a function of all this other stuff. What we're going to do, though, is we're not too concerned as far as the layer or the thickness or how the wind changes with any given 100 feet or 1,000 feet. We're more interested in the overall change in wind. So we're going to get rid of the dz on both sides and just look at the change in wind. So we're using the layer 850 millibars to 300 millibars. We'll put that into the equation. We know that F is 2 omega sine phi, and omega is 7.29 times 10 to the minus 5th radians per second. And phi is your latitude, which is 43 degrees. So that gives you an F value of 1.0 times 10 to the minus 4th, or 10 times 10 to the minus 5th radians per second. So we'll stick all of this into the equation, as well as the gas constant, which is 287 joules per kilogram per Kelvin. And we also have a temperature gradient. That temperature gradient is minus 2 degrees Celsius per 100 kilometers. We'll stick that in for the gradient. And it's time to calculate. Break out your calculator, start crunching the numbers, and you'll end up with 59.8, or about 60 meters per second. 1 meter per second is about 2 knots. So this is saying that the wind changes about 120 knots in that layer, because the temperature changes about 2 degrees in 100 kilometers. Now 100 kilometers is about 60 miles. So that's the difference between Fargo and Grand Forks about. And 2 degrees Celsius, that's about 4 degrees Fahrenheit temperature change. So a 4-degree temperature change between Fargo and Grand Forks will produce winds of 120 knot, or at least 120 knot wind change. from 850 millibars all the way up to 300 millibars. So if we use our winds at 850 millibars, we have 30 knots, and we calculated a change in wind with height all the way up to 300 millibars of about 60 meters per second. That gives you pretty close to, well, let's see, 30 knots is about 15 meters per second. So we're going to add that to our 59 or 60 meters per second. That's the thermal wind. And from that we get 75.3 meters per second. Convert that to knots, and that gives you about 146 knots. So what this is saying is, for a relatively weak temperature gradient in a layer of the atmosphere, you can get an amazingly strong wind. And this is the concept of the jet stream. The jet stream results because of a horizontal temperature gradient in a layer. So moderate temperature gradient produces a strong wind aloft. And the thermal wind is the difference between the winds at the upper levels minus the winds at the lower levels. So it's the difference. And remember that the thermal wind is parallel to the temperature gradient, with colder temperatures to the left. And that's what that's saying there. Parallel to the temperature gradient with cold air to the left. That's all for this video. The next one will continue our discussion of the thermal wind.